I always like to wait for it to kind of pop up to make sure that I did it. Oh, okay, there it goes. So I'm going to go ahead and share my screen. And I want to start with something that is probably on our minds, or if not right now, it will be. So the exam, I now have the room is confirmed. It is S206. So S206, I'm sure you're familiar with it, but it is a large enough room to accommodate all of us. And so I have not put this out on Canvas yet because I just got the confirmation this morning when I asked for it. I did want to spend, like, this is the first in the PowerPoint, so I thought I would like quickly go through it. I think that there's some value in going through what I think we've covered. And then if there's something that you're like, I don't think we talked about that, or you have questions, we can bring those up. And then I'm assuming that we'll get done with this in fairly short order, and then we will move on to our next topic. So I really want you to consider, as you're sort of preparing for it, this is a very different, this is not really a theoretical class. So there is, might be considered a little more memorization, but we also, I think, if you can kind of think about the lab or what we've talked about or the reading assignments, which I know I'm behind in grading, but consider what we've done in the lab. Also, those videos, they provide some nice information and context. And sometimes if you can kind of think about, oh yeah, that's the part that was made. Again, the observations of the components, and then lecture notes and reading assignments. Okay. And now just to remind ourselves, lab this week, come at either 8 or 9. And if you can, bring your computer. Every time I think I have the solid cast thing figured out, there's a glitch. IT gave me a fix for why solid cast was not showing up in Software Center. It worked perfectly for me. It did not work for Dr. Schaefer. And so until I know that it works, and I'm hoping tomorrow morning we can at least get solid cast on your machine, but we shall see. Okay. So the exam is going to have some fill in the blank and multiple choice. There will be some short answers and some longer questions. There's only one possible type of calculation, and that would be on the V over A. So let's kind of just go through this, and I can sort of talk about what I think is relevant. So we didn't start with talking about surfaces, but we did talk about surface. So we should be aware of what surface roughness is, specifically R sub A, and then what is waviness, and then the reasons to care. So that would be those considerations on where we might want for fluid flow and tolerance and appearance, those reasons to care that we talked about. And we should be aware of a little bit of the why and whether we want a smoother or rougher surface. We should be aware of what a tolerance is, and this is the accepted deviation from nominal. The designer sets the tolerance, and then we recognize that there is a relationship between tolerance and surface roughness. And then what is the manufacturing triangle, and what are some of the main components in the manufacturing triangle, which we get from our textbook. Okay. We also, especially week 1 and 2, looked at statistical process control. So we should be aware of what an X bar and R chart are. What is the meaning of these control limits, so that these go back to or related to the normal distribution. And the purpose of a control chart is to detect changes in the process. And again, we rely on our understanding of statistics to help us with that. How to produce this would be the process capability study. So I'm not going to ask you to set up a control chart, but you should be able to describe the process by which we go through setting up a control chart. And if you're given a control, if you're given limits, you should, and you're given points, you should be able to evaluate and say, yeah, this process is in control. No, this process is not in control. And again, where we want the specification limits compared to the control limits, meaning we always want our specification limits to be larger or wider than our control limits. And then our process capability, CP and CPK, we should be aware of the meaning of these. And again, the how to determine would be relating the specification to the control limit. Okay, so again, this would be more on using these and understanding the meaning behind these. Okay. Well, we spent probably a little more time on casting. So we do have the casting fundamentals, grain, like the cast structure, the grain size and shape, the fact that the composition of oh, there we go. I'm like, wait a minute, I know I have that someplace. You know, sort of the idea that we have compositional gradients, that we have both gas porosity and the interdendritic or microporosity. We're interested in the alloy composition, and this is going to be of both cast and wrought alloys. And so I might need to sort of highlight this when we get to the wrought section. We also need to be aware of dissolved gas and the measures that we take to minimize that, like the fact, like how turbulent flow impacts this, and then cooling rate and properties, sort of that idea that we know that what faster cooling does. The significance of Chauvenot's rule, and here we might have some calculations. On an exam, while I am confident that all junior and senior ME students can calculate the surface area of various shapes, sometimes in an exam, boxes get an interesting number of sides. So I will not have you calculate any volume or surface area. I may give you shapes, tell you the volume and surface area of the shape, and then ask about solidification time or where there's a shrinkage or something like that. Also, we know that so when n is 2 and when n is smaller, this being, again, that thin section. And then you should be aware of what the term thermal modulus is. Again, this is in your reading assignment. I think, again, casting defect, some of this we already talked about. So for the defects here, we should be aware of what causes and then how to minimize. So the gas porosity and then the shrinkage cavities. So this would be the location of the last liquid to freeze. The misrun or cold running, that's where the fluidity is not high enough and the mold just doesn't fill. And then incorrect shape and dimensions, this would be related to this concept of allowance. So again, here we have that kind of concept of shrinkage allowance and then also machining allowance. And what that term allowance is. The 3 areas of shrinkage and then how to correct. This is included in your reading assignment. And then again, from the reading assignment, sort of the cause of distortion and internal stresses, that sort of that idea of this kind of goes back to that hot tear a little bit, that how the V/A in cooling not only influences where we have shrinkage, but also distortion. Okay. Not hearing anything. So again, I cannot see the chat. So if you do have a question or a comment, please unmute and speak up. The gating system, really just the function of the gating system to fill the mold cavity and minimize turbulent flow. The following terms you should just be aware of, just pure definition, be able to either identify them on a picture or describe their meaning and any significant factors. The riser, the purpose, the likely shape and location. Likely shape is going to be simple and high V over A. And then the location, and we talked about this in some of the labs. So the location is we really want the riser to be between the sprue and the mold cavity. If it's on the other side of the mold cavity, it's not as nice of a riser, and near sort of the thick area of the part or mold cavity. Okay. Also, we talked about the pattern. While I don't think we were super specific on this, we do need to kind of recognize that the pattern may be split. It may be no internal features. It's likely to be larger. It may have draft, and we also may have some V over A concerns. So like the example I showed you where a change was made to increase the efficiency, so to speak, or decrease the amount of machining on the pattern, and then it actually influenced the V over A to a negative extent. Okay. So the design for casting, again, a lot of this we've already sort of discussed, the consideration of V over A, gating system, minimize internal stresses, the idea that we have a flash, or we may at the parting line, very important for many processes. We need a draft. We cannot have projecting details, and we cannot have undercuts, and that we want smooth thickness changes, not abrupt. Okay, so for the 5 processes, it's really important to kind of be able to know the process, the steps, the materials, how do we make the molds, how do we make the pattern, how do we remove the part from the mold, the features like size and shape, costs, the various cost tolerance, lead time, cycle time, quantity, draft. So again, a lot of that goes back to that sort of high, medium, and low. And then for each process, kind of have in mind what the advantages and limitations are for that process. I am not going to ask you this, but I always think it's helpful to have a part or a situation in mind to say, oh yeah, that was die cast, okay, and kind of have those features. Okay, so that kind of wraps up casting. And then we finished with the wrought processes, or actually, we finished with bulk deformation. And so one of the things that, again, we should be aware of is the wrought structure. This is some in 322, but what in general is it? How is it different from the cast structure? So how is the cast structure changed by hot working? You should also be very familiar with the concept that an ingot is cast and a billet and slab are wrought, meaning hot working. Wrought alloys versus cast alloys. this is mainly the composition. Cast alloys, we know, are close to the eutectic. Wrought alloys, they tend to be closer to the terminal side. So wrought alloys tend to be closer to the pure metal. Not always, but cast alloys, again, tend to be close to eutectics. The influence of metal flow on the final structure and properties. That is huge in many wrought processes. Fiber formation, this is what we talk about in forging. We talk about the fibers. And if you look at, almost any forging promotion is going to tell you and show you the fiber formation. In rolling, we call these stringers. And again, these are the inclusions and how those ductile inclusions line up and the importance and influence of this. We should be aware of hot working versus cold working, change in properties, the difference in the equipment, and then the final result in terms of strength, ductility, also surface and dimensional tolerances. Okay. So for the bulk, like wrought processes, again, basic description, like hot working, cold working, or either. And then it's kind of nice to have some example parts. So we know that for rolling, any wrought material can be rolled. So, and including precious metals. Typically, we're talking about plate, sheet, foil, but we can also do rings and threads. And then we need to kind of have in mind the advantage of rolled rings and threads compared to mainly machined or cast products. Specifically, we looked at forging and extrusion. So forging, advantages and limitation, and especially compared to casting. And so oftentimes we do talk about that. And your book talks about that. We have some terms, like we should be aware of what upsetting means, what smith forging meaning, and then drop forging versus press forging in terms of the equipment, the process, and then the result. We need to be aware of what the advantage of having flash and the significance of the location. And that's mainly because those fibers are cut. So at the parting line, which is where the flash comes out, we actually expose defects to the surface. And then our design guidelines, the amount of draft, location, the parting line, sort of the V over A concept, and then we need generous radii, and then what happens when we get thin webs and tall ribs. So for extrusion, again, our typical metal, again, including common alloys. Let's just kind of get rid of that heat treatment. The process variables, looking at, again, that temperature related to the exit speed, the temperature, and then the cracking that can occur. We should be aware of the extrusion ratio. Again, that is the area of the billet divided by the area of the cross section, how that relates to pressure, and why a shop may have multiple presses. Okay, and on that. And then in terms of the design, we should be aware of the CCD, the circumscribing circle diameter, the shape factor, that we don't need draft, and that we have a constant cross section. Okay, so I always, let me kind of get back to where I can, let me find my cursor. There we go. So, any questions on this? Okay. So I always do like to to go over it so that we can so that we all have sort of the same idea. We are going to start sheet metal now. So what we talk about now is not going to directly be on the exam. The only reason I say that is that sheet metal starts with rolled process or rolled material. So theoretically, there could be something that we talk about that inadvertently shows up. But what we talk about today is not on Thursday's exam. But the last deformation process that we will look at is sheet metal. It is chapter 4 in our text. And we kind of know sheet metal when we see a sheet metal part, because it is a thin, it looks like it was made from a sheet. Now, when we look at some of these parts, when we see the kind of deformation, and we see this, I want to kind of point out a couple areas, a couple ways in which sheet metal is different from what we've talked about before. And one of the things that while I'm sitting at this picture, we may notice is like for this part here, this lovely bracket, this location and this location, there's no deformation. All the deformation is confined. Same with here. We have deformation along the top, but the sides may have some deformation, but the bottom doesn't have any deformation. So one of the things that we see in sheet metal, and I'm going to go to the next slide, is the deformation is not uniform. There are areas of high deformation and there are areas of low deformation. And you might be like, oh yeah, great, how exciting. Well, it actually makes the process in terms of what's happening to the material a little more complex, because if some areas are deforming and others are not, we do have some of this. We realize that some areas will only have elastic deformation or no deformation. It does make modeling of sheet metal a little more difficult. But this is something that we do need to consider and do need to realize. Another issue with sheet metal is appearance is important. And so things like wrinkling become an issue. We certainly don't want to see like a real grainy appearance, and some of these things can be a factor as well. But if we also look at other aspects, sheet metal parts generally have very high surface area to volume, and they again tend to be like sort of starting on thin. So if I if I look at all of these parts have significant surface area for volume. And that, if you're kind of thinking this can be a theme in terms of looking at volume and surface area. So sheet metal parts, we do talk about plate and sheet. Generally, we say that plate has a 1/4 inch of thickness or higher, sheet is less than a 1/4 inch. And then we're not going to talk about foil, but foil is even thinner than sheet. Okay, so processes in sheet metal, or maybe I should say terminology in sheet metal is interesting, because I, as a predominantly metallurgical engineer or a materials engineer, I'm really going to be interested in what's happening to the material. So in my field and in the field of materials, we may classify or talk about processes based on the deformation. And because we're often very interested in describing the deformation, being able to model it. One of the things that we always are looking for is being able to say, what is the relationship between how much deformation you want to do to the material? So sometimes we have to come up with new material properties. Now, also though, let's kind of consider this general term. I have some relatives in normal Ohio. I have some relatives in northern Ohio, and they may talk about, oh, so-and-so works at the Ford stamping plant. We don't really say there's a stamping operation. Stamping is a general term that will sort of encompass a large number of different processes. We might say, why don't you try using a stamped part for this particular application? Well, most of us kind of realize that's probably a sheet metal part. We don't really say, oh, that's the Ford bending process, or we might say forming, but there's some general terms there as well. So I am going to introduce the terms in the way that that they often are used in my field, but I am going to be rather, but I also recognize that in different contexts, these terms are used in different ways. So we are going to sort of look at two different processes to start. One is what we would call material separation. And I am going to say that when we're talking about stamping, we generally are looking at, separation and shaping in presses with tooling. That's a lot of times when we say stamping, we kind of are, this is something that's going to be happening in presses. So we're first going to talk about material separation, which is shearing. And shearing is really the same process that happens in scissors in terms of the material is what happens in shearing. It is separation of metal using a punch and a die. We will then talk about deformation processes, and we will talk about bending. And when we bend, it's deformation around a single axis. And if we're talking about forming, that's going to be more complicated, multiple curves, axes, and is often sort of cup-like. So if I kind of come here, I even talked about this is clearly a bend. This is not. So we went from a flat shape to more of a cup or a container. Here we have quite, most of the parts over here are bending. This is not. So we might talk about, there's even a type of forming that we might call drawing, and there's no L in there, but I can't say it without an L. Whereas these are, again, a little more complicated, these auto parts. So let's talk about shearing. Shearing is where we have separation of a metal by two blades. So it's going to be in a press with a punch and a die. It actually is a deformation and fracture process. So there's no lost material, so to speak. So it's not, we don't, in other processes, we might actually remove material, not in shearing. So when we look at shearing, we first, we have the metal, the punch comes in contact with the metal, and it starts to severely deform. So the metal is pushed into the die by the punch. So the metal starts to flow into the die. The punch is forcing it down. There's a lot of deformation going on there. After you have a critical amount of deformation, which will vary from material to material, we're going to see cracks form. And then the cracks start to move around the circumference. And hopefully, the cracks meet in a clean area and we have metal separation. Okay, so a sheared part has a distinctive edge because there's a region for the deformation and a region for the fracture. So here's just a simple diagram of a shearing operation. So this would be our workpiece. It would have started out continuous. The punch starts to force the material into the to flow into the die, and then we have that deformation and fracture. So oftentimes on a sheared part, a couple things that we also may note. Notice that we do not have straight sides on either the workpiece or the, let's call it the scrap. So going on here. Also, we notice that there is a burr, and burr height is a variable that we can control. We can't eliminate the burr, but we can control the height. We also tend to have what we would call a fracture region, so and a deformation region. So a sheared edge. So I've got a couple different examples. So here we have this particular part that was sheared, and we can actually even see we've got some different colors here that we have a deformation and fracture. And so a sheared edge is very distinctive. Also, you can't really see it on this part, but in the lab, we'll be able to see it. When you have a sheared part, you can feel which edge is smooth and which edge has the burr. And there's going to be a burr on both sides. So again, we can usually tell a sheared edge. So a sheared edge is not straight. And that will influence the tolerance, because if you're creating a dimensional tolerance, if the edge is not straight, then how much the angle is will influence the tolerance. And this can be a factor in assembly. It can also be a factor in some joining processes. There's always going to be a burr. And the burr is often, the burr height is often a factor in sort of some of the quality control. The deformation region and fracture region, sometimes we call the deformation region the burnished region. So if we, again, go back and look at this diagram, the break region is the fracture and the burnished is really the deformation. I like to say deformation and fracture because that's actually what's going on in the material. So one of the key important variables is this clearance between the punch and the die. So that is going to be this distance. This is our clearance. So the clearance is important in the quality. It is going to be related to the sheet thickness and ductility of the metal. Well, that means that if we are on the shop floor and we change from we change materials and either the thickness of the material changes or there's a significant change in the ductility of the material, well, that particular press and die may not work effectively because the clearance is somewhat dependent on the situation. The clearance actually determines the amount of deformation. If the clearance is too small, then the cracks don't meet. You get, and so you get the jagged edge. If there's too much deformation, you actually end up with a larger burr. So we looked at quality, or we talked about statistical quality control. So one of the things that you might measure or consider in a stamping or shearing operation is the burr height. And as your burr height gets too large, or if you see that it starts to increase, that may mean that your tooling has worn and your clearance has gotten too big. So again, this is just a variable that we see that can be important. Okay. So again, we're running into some terminology. There's the term blank and blanking is fairly constant. And so if we say, here's a sheet metal blank, well, that generally means that that it is the inside of the cut is the part. And so, and then if we say punching or piercing, although punching is the more common term for me, then the part outside the cut is the part. So if, again, if what's inside the circle here becomes the workpiece or becomes the part, that would be called a blank, and that would be called a blanking operation. If what's inside the cut would be the hole, or is the scrap, that would be called piercing or punching. So again, if what's inside is discarded, it's punching. If what's outside is discarded, it's called blanking. Oh, there are some other ones that are kind of interesting. We have lancing, notching, parting, just a few others. But the two that we're really going to consider or care about is punching and blanking. Well, that's enough of shearing. Because we really don't have a lot of time to spend on sheet metal. And I do want to spend some time on the material property and kind of some more on forming. So let's quickly look at bending. So bending is where we have single axis deformation. And you have probably in your mechanics of materials analyzed bending quite a bit. It is, again, deformation around a single axis. And what we know is, and what we're often interested in, is how much deformation can I do before failure? And so in sheet metal, failure is a little broader than it is in, let's say, just a straight fracture. Failure in sheet metal is going to be certainly tearing or fracture. Also necking. Most of us would not be really fond if we saw a visible neck in any of our components, and then also wrinkling. So what we see for bending is that straight ductility is a good indicator for how much bending you can do. We quantify the amount of bending by the minimum bend radius. And we'll look at a couple examples of that. And I'm going to add a couple video clips about sheet metal. I'm going to put it on tomorrow's lab assignment, or I'm going to put it in the same location as tomorrow's lab. But because it's not on the exam, it's up to you on when you look at those. But those will also sort of talk about how we define the bend radius and how we define some different types of bends. So now when we talk about forming, remember, forming is more complex. We're not just deforming around a single axis. We're taking a sheet and we're making it into a cup, or we're making it into a box. So straight ductility, and remember, ductility, if we kind of think about ductility, this is percent elongation or percent reduction in area. And it is from the tensile test. And the tensile test is uniaxial tension. So because the tensile test is uniaxial tension and bending is deformation around a single axis and is tension and compression, well, that makes sense that what we get from the tensile test would work quite well in bending. Forming, on the other hand, it's not uniaxial. And so ductility really doesn't tell us how much deformation can we do. So there is something called formability. So formability is different, and we will, when we get to forming, talk about this sort of new property and be able to sort of describe it. But let's finish probably today, I'll see, with going back to bending and kind of saying, okay, we can use straight ductility to describe this. So let's look at a bending, a part that's made by bending. So just because we say that bending is deformation around a single axis doesn't mean that we can't get fairly complex parts. We just have to do multiple bends. So here we would have a blank that has been punched. And we've got the 3 holes and then the hole in the bottom that have been punched. So this has been sheared. We would actually see that sheared edge. So what we see is that we have a bend here and here. We have a bend here, and then we're starting to see these sides are bent again. So here we would have mid-process, and then we can go again. A lot of these bends are becoming, more significant. And then finally, we would have what looks like a pot handle. So this is all made by bending, and we actually look at what we call the minimum bend radius. So again, when you look at parts, if even though there are you can't see my finger, even though there are multiple directions of their shapes, each one of these was made by deforming around a single axis. So the amount of deformation that we can do is characterized by the minimum bend radius. So we're looking at like what is the radius here. And what we're saying is that the higher ductility means a tighter bend and a smaller bend radius. So a small bend radius is for a tighter bend. Now, again, we'll look at, when we talk about a hemming operation, that is sort of what I've kind of described up here. where for highly ductile materials, we can just kind of bend the piece over on its side. So if I'm looking at the sheet, it could be, are we flat like this, which would be a flat hem, that's a very small radius, or do we have more of a larger or teardrop? So that's actually something. We want to look at the orientation of a tight bend to the rolling direction. So let's look at the next one, because we'll kind of circle back and finish on a topic related to bulk deformation. Okay, so stringers, again, in our sheet metal, these are those inclusions that align, that deform and are aligned along the rolling direction. So one of the things that we see is that if we have a tight bend, that the axis of the bend is parallel to the rolling direction, well, then we see that those stringers can cause cracking, as we can see here in A, and then we see over here. So we start to see these cracks, and what's happening is that that we can actually have separation of those stringers from the other material. However, if the axis of our bend, or the axis of the bend is perpendicular to the rolling direction, then those stringers, they actually just deform, and we don't get that cracking. So this is one of those ways in which the stringers in the rolled sheet will influence, sometimes, not always, only for a really tight bend in a material, where we may need to orient that bend such that the stringers are elongated during the deformation and not, we don't see a delamination. Okay, I see that it is 9:48, so I think that this is a very good place for us to